Welcome. We are here at NASA Langley Research Center in Hampton, Virginia, and we're about to drop this 14,000-pound Orion crew module behind me as we prepare for Artemis 2, which is NASA's first crewed mission. This is the fourth test in this series and the final one. We started off by dropping it at 1.6 feet, and today we are pulling it back 135 feet and up 80 feet. And it'll hit the hydro basin here at 41 miles per hour, so we're going from very high and very fast. So today I have Brian Russ, the project manager for the test series, Dr. Mark Baldwin, Orion landing analysis from Lockheed Martin, and Jeff Suey, a load and dynamics engineer from Johnson Space Center. So if you all have any questions for us, please leave them in the comments down below, and we will try and answer as many as we can after the test. So, Brian, can you tell us a little bit about where we're standing today and what we're going to expect with this test?
Sure. Today we are at NASA Langley Research Center's Gantry facility. It was originally opened up in 1965, and its original mission was the training of Apollo astronauts for their final few hundred-foot descent to the lunar surface. At that time it was known as the Lunar Landing Research Facility. Fast forward a number of years, and it's now known as the Landing and Impact Research Facility, and it's used to test a wide array of various equipment, hardware, and flight vehicles in a whole host of various landing and impact test scenarios. Today, as Ali mentioned, we're testing the STA, which is the Orion Crew Module Structural Test Article. We will be doing the swing test. This is our one and only swing test in this series of 4. The first 3 were vertical tests. But today we have brought the crew module back to 135 feet, 80 feet in the air. And at a certain point, when we are all ready and our DASs are all warmed up, we will then fire off a series of pyro cable cutters that will release the crew module down towards us, towards the hydro impact basin. And when it gets right to about the point of vertical, we will fire off another series of explosive bolts, and that will then separate the crew module from the IP, or what we call the integration platform. And then the crew module will then continue on until it ultimately impacts into the hydro impact basin. And we expect that it's going to actually go what we call stable 2, or upside down. It may also continue over and tumble. We're not quite sure about that yet. Either way, it should be a pretty exciting test.
Thank you, Brian. And so it's going to be a pretty exciting test today. So as I said earlier, we're preparing for Artemis 2. Mark, how are you and Lockheed Martin working with NASA to ensure that Orion will be safe for a crew?
Well, I'm part of a much larger team of analysts, designers, program managers that all have worked on this spacecraft for years to get to this point. In fact, this test is really important as one of the final steps that we have to verify that the structure, as built, as designed, can withstand the impact loads it's going to see. And this test is representative of a plausible case we might see out in the ocean upon return. That could occur after an abort, so we might have a high altitude abort where we're coming down into winds and waves that are much different than when we started, or on a lunar return, we come back to the Pacific, we either lose a parachute or we see a high wind, high wave day. So this one's important because the way it's hanging, it's going to dive into the water, flip over, and that's going to cascade load through the vehicle and give us a sense of, can the vehicle withstand that? Also important is the data on the inside that we're going to collect. It's going to give us a sense of whether the crew, had they been in this capsule today, would survive and would sustain injury or not. So that's really the important part where we're at now. This vehicle has been through years of testing. We've shaken it, we've blasted it with sound, we've stretched on it with tens of thousands of pounds, and here we're about to go dump it in the water, which is important because after all that, if it still survives, we know the structure is sustainable for all the environments that we might see throughout its lifetime. And that's a critical piece for the Lockheed team and for the NASA team before we put crew on Artemis 2.
Great, thank you. So we have time for a couple more questions. So why we've gone through all these tests. So why do we keep testing the capsule?
So that's a good question. Since we're about 12 years in to the water impact assessments that we've done, we've progressively evolved these tests with more fidelity in the test article. So in the beginning, we actually did 40 drop tests where we just dropped a low fidelity capsule in the water over and over and over again. That we changed the velocity, we changed the pitch. That gave us information of how do those interior loads change as we did that. Then we stepped it up here at the Gantry with a different test series, the boilerplate test article, and that was a little higher fidelity. We did tests like this, but it didn't really have all the detail in it. Then we did what was called the ground test article test. That was a vehicle that Lockheed built, we brought here in the facility, did similar sets of impacts. All of those gave us important information, and it got progressively more complex. What you see here today has a lot of complexity in it, and that's the kind of structure that we need to understand when Artemis II flies, and it mimics really what's in there and what needs to withstand the loads.
Great, thank you. So we are actually going to move out. So we're gonna get ready for this test to get started. So if you have any questions, make sure to leave them down in the comments below. We are going to show some drone footage from our last test as our crew moves over. As we walk, Brian, can you tell us a little bit about the investment of Orion?
Sure. Back in about 2009, the Orion program actually provided a rather large investment to the Gantry facility here at Langley. And that was to actually construct the hydro impact basin here at the end of the Gantry. It did not actually exist prior to that point. And by building the hydro impact basin, it greatly expanded the capability of the facility to begin doing testing not just over the dry ground, but also water impact and testing of various crew modules. And so that also allowed us to support a number of other projects, including the NASA's CCP, which is the commercial crew program. And by doing that, we're able to support other commercial endeavors such as SpaceX and Boeing in their crew module testing as well. So we're actually doing our big part here to test both on a national level and as well as for commercial crew endeavors.
Awesome. Well, thank you. And I believe we are going to get ready for our test. So we are going to step back and watch as well. So be sure to leave a comment down below if you have any questions.
T-minus 2 minutes. T-minus 1 minute. T-minus 45 seconds.
Because he wants to hear your reaction.
15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Release.
That looks good. Come on. Great. Catch them in net. Yep. Awesome. That looked great. Standing in water.
All right.
Our
Well,
feet
that
are
was
wet.
a great test.
So-
Now that we're standing in about an inch of water, how did that look to you all?
I think it looked great. We hit the pool. It appeared that we wanted to hit 25 feet in. It appeared that we got really close. We'll find out further, when we look at the photogrammetry,
Yeah.
exactly where we hit. Obviously, we're in the stable 2 position, upside down.
Yep.
And now we wait for the IP to stop swinging before we can go and retrieve the STA.
Great. And so what happens after it hits the water?
Yeah, Ali, one of the things that we do is we try to analyze what'll happen not only at the point of impact, but as the vehicle is going underwater, how it's rotating and how it's going to end up upside down. So we do that with engineering analysis. That's what makes this job because, as you saw, when that thing's going, it's going. There's no going back. The only way we can prevent a catastrophic event is to spend the time, and that's what Jeff Suey and I do as part of our engineering jobs is we spend the time analyzing all parts of the structure. We look at any piece that could either bend, break, and that could lead to something catastrophic. Of course, we don't want that to happen when crew are on board. So we spend a lot of time trying to understand how that's going to occur, and that makes it kind of fun. You know, we have to account for the possibility that the wind kicks up or things don't go quite exactly as we planned, but that's engineering for you. That's the fun of the job, and that's the fun of working Orion.
Absolutely. I mean, that was a fun test. That was a huge wave that it made.
Yeah.
That was amazing.
Can I add on to what Mark said?
Absolutely.
So we spend a lot of time behind the computers doing analysis work, and coming out to see something like this is just outstanding to watch it happen and try to visualize what the crew would be feeling when they go through something like that. So it's really fun to get out from the analysis work and really see the test like this.
Yeah.
It's really cool.
See it in action is
Yep.
amazing, honestly. So, and for anyone who is joining, can you guys reiterate kind of what we started at and how far this capsule flew today?
So again, we actually pulled back 135 feet back from what we call the zero station here, which is right between the gantry legs, the forwardmost gantry legs here. We were 80 feet above the ground. And when we came down, when we were right above the water, when we released, we were moving at about 41 miles per hour as a resultant force into the water.
Wow, amazing. And so what kind of data are we getting from this test?
So we have primarily our sensors that are installed are accelerometers and strain gauges, and they are actually located all over the crew module, from back shell panels, the heat shield, various components interior on the pressure vessel, and other ancillary components. Mark may actually be able to provide a good insight as far as the data that you're getting from all of those sensors that are installed throughout the crew module.
Yeah, that'd be great. Mark,
Yeah,
can you elaborate?
To go one layer deeper is we have to understand when that all happened, it's a blink of an eye, right? You can't see how fast everything occurs. So what we're trying to understand is how does the vehicle, it actually flexes, it stretches, things accelerate, they bounce. And analytically, we can try to predict if that's going to happen or not, and we have to look at our models to see, did we match what we just measured? And of course, we spend all our time at our desks looking at a crew module that's this big, right? But from that, we can glean a lot of information. And it's really amazing the tools we have today to be able to help us fully understand and appreciate, okay, this is how we hit, this is as it rolled. By the way, that wasn't just a single test, what you saw. We kind of split it up into primary impact when it first dives into the water, but underneath the water, you actually rotate it, it came back up, and it came almost completely out of the water and hit back again. So those are the things we have to try to mimic in the model, and in those various situations still predict what happened and help ensure that, okay, we can withstand those environments.
Amazing. So, as you all know, we had some questions from social. And so if you have any more questions, please leave them in the comments down below, and we'll try and get to as many questions as possible. So I am going to open up. Let's see. So we have so many questions. But Jeff, can we start with you? Would you describe the system that will upright the crew module when it ends up upside down?
Sure. So as you saw, and I think you can probably see after the test, it rolls over and it ends up upside down. You can imagine the crew would be in there. They're going to be upside down, so they're going to want to upright as soon as possible. So we have an airbag system, and the bags inflate from underneath, and they'll actually allow the capsule to rotate upright.
So is this test a mock-up, or is this mock-up just for this test, or will it be converted to a flight-ready capsule?
It's not gonna, well, you can see it's still sitting upside down. We'd rather not fly that if we didn't have to. No, this one was intentionally built to be a replica of the flight vehicle, but like I mentioned before, we've poked and prodded this, we've shaken it, we've blasted it with sound. All of that, we put this vehicle through the ringer so it wouldn't have, the flight vehicle will never quite have to go through all of that at once. So no, it's not gonna fly.
Thank you. And how did Orion select water landings versus land?
That's a good question. I mean, there's some value in hitting water because, first of all, it displaces out of your way, right? And the fact that we're shaped like a wedge means we're cutting through the water. That actually reduces some of the loads on the structure and the crew. So there's a benefit. We didn't quite mention it, but when it was hanging up there, the crew would be kind of lying on their backs and their feet would be down towards the water. And that's the posture they're gonna have when the vehicle goes into the water each time, because the parachutes hold the vehicle at that angle. And there's a benefit to controlling that acceleration, where it goes and what level it is. So a lot of what you see is really by design, and that's important for us to be able to control the environment, because when you're out in the sea, winds and waves are going to catch the parachutes and catch the vehicle, and we have to try to control that. Water ends up being a pretty nice, consistent medium to hit, as opposed to the ground or sand or other types of environments.
So since we're on the subject of landing in the water, why the Pacific, and are you guys going to be able to pinpoint a certain landing spot?
We do have a target landing area. When we come back from the moon, we're going to come back a lot hotter and a lot faster. So we have to pinpoint a target location. There's a range that we likely will land in. Our recovery crews will be in that area, but it's predominantly due to the lunar trajectories we're flying and the fact that we're coming back hotter. We wouldn't want to fly in that fast over land over the United States and try to hit back in the Atlantic. So that's a primary reason.
That makes sense. Are there dummies in this capsule? How are we going to load humans onto this capsule?
We don't have dummies in this capsule. We use the space to put basically the computers that are going to record the sensor data. And so what we're going to do is we take accelerometer measurements, and we can use that data, bring that back, correlate with the models that Mark talked about, and then come up with our worst case landings. And from there, we go to a different type of test where we go to a sled test, and we can use crash test dummies and kind of simulate what the crew would go through in the extreme landing. And then we'll go on and do human testing with the sled testing at a more nominal, safer, more realistic, or more probable case, a landing case.
Great, thank you. So we've mentioned there's a lot of testing that's done on this capsule. Are there internal cameras inside? Can anything come loose on the inside?
So this particular test, we did not have interior cameras, but you can go on YouTube and watch the previous test series. It's called the GTA Water Impact Test Series. In that test, we actually had two dummies. We had a small female and a large male in suits, in seats, and we had interior cameras to show us what would happen. So that was very beneficial, and because we got that data in a similar type of test series, we were able to leverage that information, and we did not need to do it again this time.
Are there accelerometers inside? Do we know the reading of those if we have them? And do you have an idea of the force generated on the astronauts at impact?
We actually have a large number of accelerometers inside the crew module. They are actually located on the seat backs where the crew would be located, and all throughout the pressure vessel where the crew is actually enclosed. We'll use those, as Mark was saying, to correlate to our simulations. We don't have the information yet. That will be part of the that task for the next couple of days. Once we remove the crew module, we'll get it back to our integration facility here at Langley, and then we will begin hooking up our computers and downloading that data. And then once that is done, we will then provide it to both our engineers here at Langley and at Lockheed, and they will start pouring through it and analyzing it and correlating it to our expected values that we're looking from their various analyses efforts.
Thank you. And so we're about to wrap up, but I have one more question. Which test is this for? Is it for Artemis 1 or Artemis 2?
So I can speak to that. It's really for all of them because we expect, since we only could run 4 tests this time, we're going to have hundreds of thousands of possible landings that could occur. Artemis 1 is coming up soon, and we'll get data for that landing. But what happens, and this is, again, the fun of the job, is we're going to take these 4 data points and we're going to try to interpolate what that means to all possible landings. So really, what we're doing is we're learning from our models, and it doesn't matter which mission we're looking at, we're going to have the information to be able to predict what will happen in any of the missions. So it really expands to anything here forward for the Artemis landings.
Great, thank you. And thank you guys for joining us and answering all these wonderful questions that you all commented, and we appreciate it. So please be sure to follow Orion and Langley on all our social media platforms. If you want any updates, be sure to check out Orion's page on nasa.gov, and we'll see you next time.